our next talk, Stephen Belanger, who's going to give an amazing talk. He works at Datadog. And on the Node.js, you're with APM Dev. Is kind of your role on Node.js. Is that correct?
Yeah.
So, big round of applause for our next speaker, Stephen Belanger. Take it away.
Hello. I'm here to talk about observability with Diagnostics Channel and AsyncLocalStorage. So, hi there, I'm Stephen. Involved in Node.js core and diagnostics working group for many years. Build diagnostics tools at Datadog. My pronouns are he, him. So let's build a tracer. So I'm going to walk you through how a modern tracer works, just to give you an idea of like how we're gathering data and how you can help us make that easier. So first of all, what is a trace? So it's a collection of spans. Each span has a start and an end time, and some contextual data describing what the span was for. So in this case, there's a web request. It's making a GET request to some API route. And spans can also contain, well, they can also have like any number of child spans. And so like that describes a relation to like the next request was caused by the web request. The code representation of a span looks somewhat like this. It's a container to hold contextual data about like what's going on, and each span will have like a span ID, a trace ID to link related spans together, like to like group all the spans of like a request together, and then a parent ID to link to like what the parent was, and like generally you should like use the parent ID instead of linking directly to the parent, because if you like link the actual objects, then you can use a lot of memory and can in weird cases cause memory leaks. So don't do that. And then when the span ends, like it'll compute a like duration or like do timestamps at the start and end. Every tracer does it a little differently, but you're trying to measure some time and then report the final result to your tracer. And different tracers implement it differently. So some will, like for each span, will stream out the span to somewhere. Some will build up a trace representation in memory and then like make some decision after the fact if this was interesting enough to report or things like that. So how do we, like, we have this span class, how do we actually build stuff with it? So there's an API for that, several actually. So Diagnostics Channel, it's basically a high performance event emitter that's focused on just emitting lots of just generic diagnostics events about anything. It doesn't really impose so much structure on what that looks like. There's tracing channel, which is a layer on top of that, which aggregates a few channels to represent the concept of this span. And then there's AsyncLocalStorage, which does a completely different thing. It like helps you share data like across a request, but that lets us link things together, and I'll explain that one a bit later. So first of all, what is Diagnostics Channel? So you have this API that's it's sort of like an event emitter, except you create this channel object ahead of time, and then you should generally include your module name, just because this is like a global namespace, so all channels across everything is going to use the same namespace. So put your module name in there, please, so you don't collide with someone else. And it's designed so that you can publish like very liberally. So a normal event emitter, you normally emit with the name and the data, and because you pass in the name, it has to actually go and look up like where are all the handlers for this name. But with having a channel object, it doesn't have to do that lookup. It's just like on thing here is a pointer to the channel. So V8 is smart enough to just go and find it. So it's a lot faster. And each channel should have a single object structure. So if you find yourself like wanting to communicate different like structures of data, you probably want to have multiple channels. And so publish is near zero cost until there's a subscriber. So if there are no subscribers, then the publish actually does nothing. It doesn't actually check if there's anything to publish to. This model with the like putting things in like a named channel and then we subscribe somewhere else allows us to decouple tracers from the libraries. So like we don't need to have like some interface that like we pass our tracer object into your module or something like that. It's like there's some libraries have added support for like certain tracers, and they have to like do a bunch of extra work to like have an interface to receive this tracer. But yeah, you don't need to do that. Just published events, and using like Diagnostics Channel events allows us to eliminate monkey patching. So for a long time, APMs were heavily built around, we would just patch everything in the environment. And that is not particularly safe, especially across versions. Like a lot of APMs, like we have to support versions of modules like going back years and years. And like these are gonna evolve dramatically over time. And so we have to code extremely defensively to make sure that it's like we don't break a future version of things like that. It can be challenging. So let's look at an example. So we've got the channel at the top. We're publishing some data like after we've like called the set immediate and called its callback. And we have this has subscribers thing to avoid object construction. So the publish, if there's no subscribers, and the publish itself has like virtually no cost, but sometimes the object construction can have a bit of cost. And so like if you're calling something very, very frequently, you might want to use has subscribers just to make sure you're not spending cycles you don't need to spend. And you can also subscribe directly to the channel objects. And yeah, so behavior of how to react to the event is delegated to the subscribers. So like in this case, we have this thing. It's like doing a thing. We might want to aggregate like how many times did it do a thing? How much time has it spent doing a thing, or things like that. Like you can delegate that to the subscribers. They can just decide how to react. And we recently released this polyfill, DC polyfill. It includes like the most recent version of the API. So this matches what's in like Node 21 now. Like it's designed to use the core features where available, and then layer the new stuff on top of that. So if you're using, say, I think it's like Node 16, Diagnostics Channel was introduced, but Tracing Channel was not there yet. And so, like, with this, we will layer all of that on top of it, and so you just get this like modernized version, but it still actually uses the internal Diagnostics Channel, so you still get that benefit of the like global sharing of channels. And this is behaving strangely. So it's layers on like any missing functionality, and if you're on an old enough version, the Diagnostics Channel doesn't exist at all, we'll re-implement the core itself. But if you're on one of those versions, then like you're only going to get it out of our library. So there won't be any node core events or things like that. So what about Tracing Channel? So it's a group of multiple channels to represent a span. So there's 5 correlated channels. There's a start and end around the synchronous part of calling something. If it's an async call, then there's going to be an async start and async end around the callback, or like promise continuation, or like I don't know, some future async thing. And then there's errors. And so you can selectively listen to which channels you need. It's like a lot of vendors like might not care about particular events. It's like most tracers, they consider the end of the span to be the async start. That's when the callback is reached, and then it's now something else. So the async end we mostly don't listen to. Yeah, each of the events, like a single traceable action, will share a single object, which it'll emit this same object to each of these channels, and you can use that object reference equality effectively to correlate the events to each other, or just stuff things into the object. And then errors get added, and then it as a property of this object, and then it gets emitted to the error channel. And there's a result property that gets added. So, but before the end, if there's a sync function, it'll add the result property for representing the return, and then if it's a callback, it'll add the result before it runs async start. So tracing channel. So this is what it looks like for synchronous code. So we've got this trace-sync function that's it wraps a synchronous call. So here it's wrapping the square function. So the second parameter here, it receives context data. So we've given it this object with the input, so we know what this what value we're passing into square. And this will handle the start, end, and error events. It'll just wrap those automatically. And we can, it immediately invokes this, but we can also optionally pass in this and input arguments if we want to do that. And also passes through the return value. So this is roughly what it looks like internally. So as you can see, we create this message object, the context object, and the start and end kind of creates a scope around the trace, and this calls that original square function in the try branch there, and the return value is captured on the result, which we can then see in that on end later, and thrown errors are added to the message and viewable and on error. So the tracing channel for callbacks looks much the same, but there's it wraps the callback call, or the function that receives a callback. So it's handles the start, end, and error the same way, and there's a callback position indexes either way, so you can do index positively from the start, or you can do the callback last pattern. You can just do -1, and receives the same sort of context object. It also scopes the callback in the async start and end, and passes through inputs and outputs the same. So this is what the trace async looks like. So it's the sync start, end, and error look basically the same. It's just what's in that try part that's different. So it wraps the callback with a bunch of additional logic that it captures the callback error and result, and will publish the on error if there's an error, and then async start and async end run as a scope around the callback. And then we have tracing channel for promises. So you can wrap like any promise returning function, and this will have the same events as with callbacks. Passes through inputs and outputs the same. The one thing that's is a little bit weird is the async end runs immediately after the async start, and this is because promises are infinitely chainable, and so there's not really an end to them. So there's not really a good place that we can decide, like, yeah, here's the async start and then a bunch of stuff, and then async end, where does it go? Somewhere. So yeah, it just runs immediately. So this is roughly what it looks like internally. There's, yeah, again, start, end, and sync are the same. The promise resolution in this case is stored in the result, and promise rejections get stored as the error, and then the async start marks like when it's resolved this promise, but also runs the async end immediately because, like I said, it's infinitely chainable. There's not an end, and so that shows us how to like talk about like what the process is doing. So what's this async local storage thing? So it's a storage system. I like to describe it as like lexical scope, but by call path. So in this example, you can like call B from A because like B is available in this lexical scope, but you can't reach this thing from B. However, like you could just pass it as a parameter in this case, but sometimes things are a bit more complicated. So here there's this module you don't control. Calling B triggers this something event. There's no way to pass data through this B function. You got this from somewhere else, and you've no idea what happens in this B. It could do a whole bunch of async stuff somewhere and then come back to you. Who knows? So can you attach the like thing to the emitter maybe? Can you store it globally? No. Concurrency will override it. So this sort of scenario is where async local storage helps. So you can propagate through calls without needing to pass like anything into that call. So you call this. So you construct async local storage instance, and then you call this like store.run, and you give it some value, and that value will be accessible anywhere that is logically descending from that execution. So the function given to run works as a scope to say like anything that happens within this scope is like should attribute to this, and then yeah, you can get the store at some point in the future. So like eventually be led to emitter on something getting called, and so thing store.getStore was able to get foo out of it there. So as long as a causal path can be drawn of execution from the start to wherever you want to get to, async local storage should flow through that. So here's a more concrete example. So say that there's like this static serving module, like it's just like serves a file and it has like some like log function just to tell you like, oh yeah, like it's trying to load the thing, and yeah, now it's loaded, I'm going to serve it. So this is like this is designed in a way that like you would use this at the top level, and just pass in like the base and the log function, and you would just run this for each request. with async local storage, this module doesn't actually need to care about. In here, there's the two loading messages. Like, you might want to correlate these two. It's like loading this path name, done loading this path name. Well, what if you get it like two concurrent requests? Like you don't actually know which requests these loading things came from, so you can't actually correlate those messages. But with async local storage, we can make a custom log function that so we wrap the running of the handler in this ID store, where we generate an ID for each request, and then in the log function we can go and get what the ID is for that request, and just provide this modified log function that just includes the request ID in there, so we can easily do this correlation without the library we're using actually even supporting this concept. So how do all these fit together for the purpose of tracing? Async local storage has this, Diagnostics Channel has this handy thing called bind and run store. So it maps channel events to store updates. So the run stores suggests a state, suggests a state change for a scope to accept. So it's optional. So this is essentially just saying, like, async local storage, you might want to do a run around this, maybe, but it's produced as a Diagnostics Channel event, and then the other side can accept it. So the bind store is what does the accepting. So in this case, we've done the run stores on this channel, and then we have multiple things can bind to that. So we've bound ID store to generate, I want to generate an ID for each of these requests, and we've also separately bound, I want to track what the URL is for this request. You can bind any number of stores, and each store can have its own separate decisions on which things do I actually want to bind to, and how do I want to transform the events that come in, because but by default it will just take the event data and make that the store content directly. But if you use this transform function, you can receive that and then return your transformation of that. So in the case of APMs, we use this to create our spans. So the transformer stores a new span as the state of our span store. We can link, so this is where async local storage helps. We can link the new span to the parent span by just getting the current store while we're about to set, with the transform, set the new value for the store. And then if you want to say scope the trace concept around a request, which is what most APMs do, you can just omit the parent link in that particular case, and that'll make it basically a root span. So you'll be able to get the current span anywhere descending until this store state transitions. So when that trace sync happens, then there's going to be a first span that's created, and you can access that up until the trace async creates a new span, and then inside its callback, it will have that new span as the current span. You can also use it to recover lost context, which sometimes async local storage is currently layered on top of async hooks. I'm working on making it not do that, but the design of it sometimes will not follow, it'll not follow the path you expect it to, because there needs to be, in certain cases, some instructions to tell it that it needs to follow a certain path. We, as APMs, occasionally have to recover the context in some way, or any sort of user of async local storage may have to recover the context. so in the start event here, we can store this span on the context, like on the message, and then because that same object is shared between all of the all the different events of that traceable action, we can retrieve that from the message object in future events. So we can bind to the async start, which is the start of the callback scope, and set the this does the bind store and transforms to what that message, what span was stored on the message, so that'll re-scope that callback to what we think it should be instead of what AsyncLocalStorage thought it should be at that point, maybe incorrectly. And sometimes people are going to have different opinions of what the scope should be, so that this also lets people have those different opinions of what the scope should be. Then you can also trigger the end of a span from either the span stored on the message or the span you retrieve from the store. It's up to you how you do that. And as I mentioned before, there's different interpretations. Most APMs consider the async start, when the callback is reached, to be the end of the task, but some consider the task to be part of part of the overall span. This is flexible enough that either interpretation is valid. You can do it just fine. So congratulations, we now have a working tracer, and I hope this has helped to demystify how these components fit together, and gives you some ideas of how you can use Diagnostics Channel and Tracing Channel in your own modules. And if you have any further questions about it, feel free to ask.
That's great. Thank you so much. Any questions? We have a few minutes, if Steven's okay. Any questions for him? We can take those offline too during the break. Steven, thank you so much. Great talk, and so excited to see the progress around tracing and performance in Node.js. This is what I love about Node.js, right? It's a framework that's been around for a long time, but we have all this amazing stuff that's still happening between the test frameworks, the tracing, so much amazing stuff happening. Thank you so much, Steven. Appreciate your talk.